While hierarchical usage of switches for building a LAN is possible and in use, there are some implications regarding security, privacy, and efficiency that you should consider before using a single LAN to connect all devices within an institution. A LAN connected using a hierarchy of switches is a single broadcast domain. While traffic among connected hosts to a single switch in the hierarchy could be kept local, the broadcast nature of protocols running in the LAN for unlearned destination means frames traverse across the whole network. This might not be a best choice in terms of security and privacy. Limiting the scope of broadcast can also help improve the performance of the LAN. Managing users and connecting them in a hierarchical way to partly isolate single switch traffic in this design is only possible through physical connection. For example, if you have a LAN connecting computing science, computer engineering, and electrical engineering departments in a hierarchical way, as you can see in the figure, if a computer science user moves office to electrical engineering but wants to stay connected to CS switch, the solution remains at keeping the physical wiring to the CS switch. This might also not be an effective isolation scenario due to varying number of users in each section, making it harder to realize using same small repeatable commodity switches. To remedy this, we can use switches that support virtual local area networks. In virtual local area networks, known as VLANs, switches are configured to support multiple virtual LANs over a single physical LAN. To do this, port-based VLANs could be employed. Using port-based VLANs, ports of a single switch are grouped together. Each group forms a VLAN over the single physical switch they're connected to. For example, in this figure, VLAN ports 1 through 8 could be used to make one VLAN, for example, electrical engineering VLAN in our institution network example, and ports 9 to 16 to make another VLAN, for example, computer science. This emulates the behavior of two separate physical switches, each working with 8 ports. Frames to and from ports 1 to 8 can only reach ports 1 to 8, and the frames to and from ports 9 to 16 are local to ports 9 to 16. This eliminates the need to change physical wiring when moves happen. Only changing port membership in each of the virtual LANs would be enough to modify VLANs as necessary. The VLAN-capable switches are enabled to isolate the traffic between the port-based VLANs. Ports can be dynamically assigned among VLANs and change the isolation settings. However, to make the isolation happen, the traffic among the VLAN ports need to be routed among VLANs as if in physical LANs. Remember, when we had different local area networks and we wanted to send a packet across them, we needed a router with a port connected to each of the LANs. This means that layer 3 forwarding is required at the connection point of the LANs. That is why the VLAN-enabled switches provide basic routing functionalities to be able to process up to layer 3 so that they can forward datagrams among their port-based VLANs. Another interesting and very useful setting that we can gain using VLAN-enabled switches is configuring VLANs across multiple switches. This would require a port that connects two switches, but parts of them are virtually seen as one. This port is called a trunk port and carries frames between VLANs defined over multiple physical switches. We discussed VLANs, but we did not mention what defines the belonging of the ports to the same group. This becomes even more important when spanning VLANs across multiple switches. how do we define the membership of ports of multiple switches to the same group of ports making a VLAN? This is performed using a VLAN ID. The frames forwarded across the trunk port carry a VLAN ID that identifies to which VLAN they belong to. For example, in the same example, on our first switch, we use VLAN ports 1 to 8 for electrical engineering. We use ports 9 to 15 for CS. We use port 16 of the first switch as the trunk port to connect to port 1 of the second switch. On the second switch, we use ports 2, 3, 5 for electrical engineering VLAN and ports 4, 6, 7, and 8 for CS VLAN. When sending packets from our first switch to the second switch, we tag our frames with the VLAN ID. So when arrived at the second switch, the switch knows to which group of ports it does belong. How do we use that VLAN ID? Remember the Ethernet frame we previously discussed? 802.1q standard extends the Ethernet frame structure to include a 2-byte tag protocol identifier and a 2-byte tag control information that includes a 12-bit VLAN ID. The tag protocol identifier, also known as TPID, uses the hexadecimal value 8100 to indicate that it carries an 802.1q frame, defining the VLAN tagging used. The VLAN ID is the identifier that indicates the VLAN belonging. There are also 3 bits called Priority Code Point, or PCP, which are used for priority indication, and 1 bit called DEI, or Drop Eligible Identifier. These bits, if used, could together also add the possibility of prioritizing different classes of traffic.